Okay guys, in this video I will discuss about the shear lag effect of a tensile member which is connected with its one leg only, either by using bolt or any weld. Okay, so if you're new to this channel, please do subscribe and also don't forget to press the bell icon so that in future you can be benefited. Okay, at the very first, this type of tensile connections are normally encountered in this type of braced connection. Here you can see this is a gusset plate and this is an angle. Okay, this is a single angle section, and when this angle is connected with this gusset plate, you know that only a single leg can be connected. Okay, and this single leg is known as the connected leg, and this is which is not connected, it is known as outstand. Okay, now let's try to understand how shear lag effect actually occur in this type of connection. Okay, and what are the different parameters that affect this shear lagging effect. Okay, so first simply stretch out your hand. Okay, so let's say this is your hand. Okay, now let's pull this particular finger. Okay, simply pull this particular finger. Okay, now what are you feeling? Of course, you are feeling stress in this location, and at a distance here you are feeling a less stress now here, and in this location maybe throughout the cross section of your hand you are feeling the stress. Okay, now again, if you are, let's say, pulling this finger and this finger, these two fingers, what will happen? This location is stressed, this part is also stressed. Now you are feeling a stress for a wider region in your wrist, and here now the whole cross section is again stressed. Okay, now again simultaneously pull this three finger. What will happen? This is stressed, this location is also stressed, and this is also stressed. Not only that, now this whole region is stressed, almost the whole wrist is being stressed, and here it is almost completely equally stressed, right? This is known as shear lagging effect. Okay, now again try to understand the physics behind it. Okay, so now when you are only pulling this particular finger, this stress is being generated like this. Let's say this is the complete cross section of your head. Here the stress is complete. Okay, so you can see as the length is increasing from the application of the load point, this stress is being spread out for a wider region. Okay, closer to the application of this load, less wide this stressed zone, but as you go away from the application of this load application point, this is becoming wider and wider. Not only that, if you have multiple load application point, or if this load application point is wider, then also this development become quick. Okay, now try to understand or try to correlate this thing with our section. Okay, so here this is an angle section and it has been connected by using some bolt. Okay, now when we are applying this load like this, okay, so this is actually the wrist part of your hand, and this is actually the finger part. Okay, so this is the finger part. So now definitely you can see that all the finger is not being pulled simultaneously, right? Let's say these are the 5 fingers, only a single finger is being pulled. So naturally here in this location there will be no such stress. Okay, now as you go away from this application point, load application point, okay, the stress is being applied for a wider part. Okay, nearest to the load application point, this width is very less, but to the farthest point here, it has been stressed, the whole cross section has been stressed uniformly. So this is B2. Definitely as L increases, B2 increases. Okay, this is one case. There is also another case. What is that? Well, you can see in the previous case, as we increase the number of load application point, or indirectly as we increase this width between load application point, this development of stress region also increased, right? Well, so here you can see that this is the farthest point which is not stressed, and this is the point where load is being applied. So if we decrease this length, okay, in that case also this stress development occurs much quickly. So if we simply compare this with a weld connection, in this bolt connection, this is the point of load application and this is the farthest point which is not stressed. But in case of a weld connection, this is welded, this is welded, and that side also welded. Okay, so from this farthest point which is not stressed to this point of load application, now this width has been reduced, so this stress development will occur much faster compared to your weld connection. Okay, so this is the basic behind shear lag. Now how we use this concept into our design aspect, whether it is a AISC table or it is a simply Indian code IS 800. Okay, everywhere to calculate the rupture strain we need two cross section. First cross section is this one, which is connected leg, and second cross section is this one, which is the outstand leg. Now in this connected leg we are only bothered about the net cross section and we need to find out the rupture strain, whereas in the outstand leg we are interested about the yield capacity of this outstand leg. Now to find out the yield capacity of this outstand leg, we need to find out the gross cross sectional area of this outstand leg. Okay, but here you have seen that the whole cross section or the total cross section of this outstand leg is not participating or is not being stressed. Okay, why? You know the reason. So we need to consider a certain percentage of this cross section. Now what is the percentage of this cross section? Well, if total gross section of this outstand, okay, O stand for outstand. If this is the total cross section of this outstand leg, we need to multiply this by some factor. Let's say this is beta, and this beta factor is nothing but the shear lag factor. Now, of course, this shear lag factor is affected by, yes, this length. As you go away from the point of load application, this width, it is increasing. It is clearly visible. So it is a function of connection of the length, and as the length of the connection increases, this width become full. Okay, so as L increases, the beta actually is being reduced, right? Well, not only that, as you know that once we reduce this shear width, okay, this is known as shear width, BS. This is the point of farthest point which is not stressed to the nearest point where load is being applied. If we reduce this Bs, in that case also this width or this stress development become quicker, which was the case of weld connection. Okay, so once Bs is reduced, actually your shear effect also increase or lagging effect decrease. Okay, so beta is a function of length of connection LC and this shear width, that is Bs. Okay, so now it is clear to you how this Bs, which is the shear width, here you can see in this figure, Bs is, it is bolted connection and this is the farthest point which is not stressed. So what is Bs? Well, it is this length plus this length. That is why Bs is higher in case of a bolt connection compared to your Bs in case of a weld connection. As weld is applied here, so this is the farthest point where it is not stressed. So now W is only this much. So Bs is larger in case of a bolted connection compared to your weld connection, right? So in case of a bolted connection, Bs is larger, so it is negative. That means beta is less. As beta is less, our gross section become also less. We are utilizing less material. Correct? Now come to the LC. Here you can see that beta is a function of LC by this. Okay, so once from this formula it is clear, if LC is large, beta is LC is large means this total component become less and beta become higher. Once beta become higher, total AGO also become higher. That means we are utilizing more material. Okay, that means once we increase the length of the connection, our development of space become much uniform. It is also clearly visible from this picture. Okay, that is all about the shear lag. If you like this video, don't forget to share it.